thank you for standing by. At this time, all participants are in a listen-only mode. During the question-and-answer session, you may press star 1 if you would like to ask a question. Please continue to stand by as today's conference will begin momentarily. Thank you.
Good morning. I'm Jane Platt with the newsroom at NASA's Jet Propulsion Laboratory in Pasadena, California. The topic of today's Media Telecon, the very first in-depth science results from NASA's Juno mission. Juno arrived in orbit around Jupiter on July 4th of 2016, and today we're going to find out some of its dramatic discoveries about the planet. We'll hear brief presentations from 5 speakers, and then we'll take reporter Q&A. If you do have a question, please press star 1 to be placed in the queue. And you can follow along with the visuals as the speakers give their presentations and answer questions at www.nasa.gov/feature/Juno teleconference, one word. Again, www.nasa.gov/feature/Juno teleconference. And a reminder that as they go through the images, you can click on a picture to get it full screen on your computer. I'd like to go ahead and introduce our speakers. We'll be hearing from Diane Brown, the program executive at NASA headquarters in Washington, And then we'll hear from Scott Bolton, the Juno Principal Investigator at Southwest Research Institute in San Antonio, and Jack Conerney, the Deputy Principal Investigator at NASA's Goddard Space Flight Center in Greenbelt, Maryland, Heidi Becker, the Juno Radiation Monitoring Investigation Lead here at JPL, and Candy Hansen, the Juno Co-Investigator at the Planetary Science Institute in Tucson, Arizona. Let's start things off with Diane Brown. Diane?
Thank you, Jane. We're very excited to be sharing these first major discoveries from Juno, our solar-powered spacecraft orbiting around the king of the planet. Juno has now completed 5 science passes over Jupiter and has provided amazing images and science data. Members of the public have been actively participating in the mission by using the JunoCam data to produce beautiful and creative images for us all to enjoy, and we'll get to see some new ones today. Juno launched in August of 2011 and is one of 3 currently operating missions within NASA's New Frontiers program. As Jane mentioned, the Juno team got to celebrate with our own fireworks last 4th of July when we got into orbit around Jupiter. The results being announced today are just the beginning as we look forward to even more exciting science as we go forward. I'm now going to hand it off to Scott to provide the science highlights.
Okay, thanks, Diane. It's great to be here. It's exciting to be able to share what we've learned from some of these first passes by Jupiter. And I'm really excited to tell you all the news that we've got. So I'd like to talk first to the first image, Scott Bolton 1. And so here I'm going to illustrate really how Juno works. So Juno flies over the poles of Jupiter, and it goes very, very close to Jupiter, just within a few thousand miles of the cloud tops. It's traveling very, very fast. It takes only about 2 hours to screen past Jupiter. So the way it really works is every 53 days we screen by Jupiter, dropping down from the North Pole and going out of the south. And we're going so fast that that whole pass from North Pole to South Pole is about 2 hours long. And most of our science is collected during these very close passes. And that's really what's unique about Juno, is because we get so close to Jupiter and we cross over both poles that allows us to see very new things and unique things about the interior and how the magnetosphere works. And so today, what you'll hear is what we've really learned from our first 2 close passes by Jupiter. We'll also share some more recent data, including our latest images that came down last week, some observations of interplanetary dust and Jupiter's rings, and you'll hear some recent sounds from Jupiter that are actually quite unique. So as I go through this, the general theme of our discoveries is really how different Jupiter looks from what we expected. So Juno, in many ways, is looking inside of Jupiter for the first time and close up and personal. And what scientists expected was that Jupiter was relatively boring. It's uniform inside. And for decades, scientists have assumed this, that if we drop below the cloud tops, below where the sunlight reaches, that pretty much Jupiter was all uniform inside, and it really didn't matter where you looked, it would all look the same. And what we're finding is anything but that is the truth. It's very different, very complex, and we're going to share those with you today. So I'd like to go over to slide 2, Scott Bolton 2, and here you see an incredibly beautiful picture of the North Pole of Jupiter. This is created by amateurs that sign on to the Juno website and make our images for us. This one's unique in the sense that each time we pass over Jupiter, because we're going over the poles, it's half sunlit, half dark, half night side. And what somebody has done here is they've actually stitched together pictures from different close passes of Jupiter so that you could see the whole thing sunlit. And what you see is incredibly, just complex features, these cyclones and anticyclones all over the poles. That wasn't really expected. The bluish hue is probably real. And the biggest feature is that Jupiter from the poles doesn't look anything like it does from the equator, or from what our usual picture of Jupiter has zones and belts, the great red spot, and we see these stripes, and that's the Jupiter we've all known and grown to love. And when you look from the pole, it looks totally different. In fact, if you look at this picture and somebody had shown it to you a few years ago, I don't think anybody would have guessed this is Jupiter. So the fact that there are the number of cyclones that you see at the poles is really something new that we didn't expect. And the fact that the North and South Pole don't really look like each other is also a puzzle to us. And so scientists are working to try to understand how these dynamics work and why Jupiter looks the way it is. And of course, we're also wondering whether this is a stable configuration. We've only gone over a couple times, and the question is do these storms or cyclones that we see here, are they stable? Are they going to stay the same way for years and years, like the Great Red Spot, which lasted 300 years at least? Or is this something that's dynamic? And of course, only time will tell us which one is true. Okay, so the next slide, slide 3, Scott Bolton 3, shows you a scientific and artistic expression of what the inside of Jupiter might look like. And so these are cutouts of Jupiter from the top all the way down to the middle of the core. And this represents what a lot of scientists believe Jupiter looked like even before Juno got there. In fact, a lot of our mission was based on some of these kinds of figures. And what Juno is about is looking inside of Jupiter pretty much every way we know how. So we have 3 different techniques to look into Jupiter. One is the gravity field, which sees all the way down to the bottom where you see ice rock core. And you're looking at like 40 megabars, 40 million bars of pressure. And 1 bar of pressure is what we feel at Earth at sea level. So that's the atmosphere of the Earth at sea level pushing down on you. So in the middle of Jupiter is a much, much higher pressure. So if there is an ice rock core, the rocks at the middle of Jupiter don't look like the rocks in your backyard. We have a magnetic field experiment that looks into that bluish region that's called metallic hydrogen, and that's where the hydrogen is squeezed so deep, so much, and the temperature is such that it actually behaves more like a metal, and it's like a liquid metallic hydrogen. And we believe somewhere in there, maybe the magnetic field gets created, or maybe above that where there's enough charged particles. But the magnetic field kind of penetrates into that. So, and then at the top part of the atmosphere, just on the right, you see a cutout called meteorological layer. That's sort of the upper atmosphere where the clouds and the upper atmosphere's dynamics. It's actually quite deep. It goes down hundreds or even 1,000 kilometers deep. And we've never seen that. And we have a new instrument that was pretty much invented for Juno called the microwave radiometer, or MWR, and it looks into that region. So we have these 3 ways to look into Jupiter. The top part is done with the microwaves, the middle part is done with the magnetic field, and then the gravity looks all the way down to the center. And so now what I'd like to do is show you a little bit of the new data and what we've learned from this MWR the first time we passed through. So go to Scott Bolton slide 4. And so here you see on the left-hand side an image of Jupiter from Cassini, I think it is, and it shows you the Jupiter that we all are used to, the zones and belts, the stripes, and then you see the Great Red Spot. And on the right-hand side, you see some of the new microwave data. And what you're looking at here is that at the far right side of that, the top of it, is sort of the cloud tops. And then the part that turns orange at the bottom of it is looking deep about 350 kilometers down. Now, in between that, what you see in the red, the white, and a little bit of bluish hue, those are indications of how much ammonia is present, or the abundance of ammonia. So orange means it's very abundant, yellow means a little bit less, white is even less than that, and blue is the least amount of the ammonia. And so at the top, there's very little ammonia, and the ammonia starts in. But the most startling feature of this that was brand new and unexpected was this sort of column that you see of orange, where you have a band of ammonia around the equator of Jupiter. It's in the zone. It's very deep. And in fact, this was completely unexpected. You have a deep band of ammonia that goes from the top of Jupiter as deep as we can see. I mean, it goes down to 350 kilometers here because that's the limit of where we're looking. It may penetrate even deeper than that. So that was a new thing that we learned just when we first looked at this data and saw it for the first time with MWR. The other thing that's new about this is that in general, you see that the ammonia peaks across all latitudes pretty deep, all the way at the bottom. And what scientists had expected was that that would peak and be uniform much further up, near where we thought the ammonia clouds were going to be forming. And then finally, you see that there's a lot of variation with the ammonia in latitude. There's some bluish parts in the mid-northern latitudes. There's different yellows and oranges that are showing up even at the high latitudes. And what this is telling us is that Jupiter's not very well mixed. It's not all uniform inside. The idea of once you drop below the sunlight that everything would all be uniform and boring and mixed up was completely wrong. It's actually very different depending on where you look at. And this is a brand new result. And this, in fact, addresses some questions that we've had for decades. About 20 years ago, we sent in the Galileo probe into Jupiter to measure its composition and to learn about its atmosphere. At that time, scientists thought that once you went through the cloud tops, you would basically see, the same thing, and no matter where you looked, it would look the same. But in fact, it came back with surprising results that people didn't completely understand, and one of the assumptions was that the Galileo probe just happened to go into a warm spot, and in fact it did look warm where it went in, and maybe that was unique. And what we're finding is that many parts of Jupiter are unique, and if you had stuck in 3 or 4 probes into Jupiter in different places, you very likely would have gotten 3 or 4 different results, and you wouldn't have necessarily known what to make of it. And so only through this new look that we see with MWR do we realize how variable this giant planet really is beneath its top layer of clouds. And that's really going to force us to rethink not only how Jupiter works, but how do we explore Saturn, Uranus, and Neptune if they're highly variable like this. We may need some kind of technique like Juno or maybe the next generation of these kinds of things where we can look beneath the clouds globally to understand how things are varying. You'll also note that the whole signature of the zones and belts doesn't seem that apparent in our data, and that puzzled us and surprised us. So the zone and belt structure either doesn't penetrate all the way down, but you can see there is some structure, it just doesn't correlate to the zones and belts, and so it evolves to something new inside of the planet, other than maybe right near the equator where that ammonia band is. And so that was a surprise to us, and we've learned that these zones and belts, either don't exist or this instrument isn't sensitive to it for some reason, but we don't understand why it wouldn't be. And so you really see this new picture of Jupiter in this data, that it's very dynamic underneath the surface of the clouds as you penetrate down, and there's this strange band at the equator. Now, we have it almost looks a little reminiscent to the Earth. The Earth has something called a Hadley cell, where we have a tropical band around the equator, and then we have the subtropics just above that. Those are dry, the tropical band is moist. Jupiter looks a little bit like that in this ammonia, but it couldn't, it's unlikely for that to have worked the same way the Earth does. The reason the Earth has a tropical band is there's a surface underneath the atmosphere that allows for a return flow. And so that, you either have an ocean or land underneath, and that allows for us to create these cycles and circulation cycles and create these dynamics at the Earth. Jupiter's gas all the way down. So while it might look a little bit like the Earth, it can't be working the same way. And so that was a big surprise to us. It is possible that this band penetrates all the way down into the middle of Jupiter. I mean, we don't know. And eventually, when we combine all of our magnetic field and gravity field science and get more microwave science, we may be able to tell something about how this band is working and how it's being formed. Okay, so I don't have another figure for this, but I wanted to touch on the gravity field, which I think there's sort of a general theme that we're seeing, that the inside of Jupiter works very differently than people had assumed. It's much more complex, and there are motions deep inside that people hadn't anticipated. And the gravity field is consistent with that. When we went to go measure the gravity field, what we were really looking for was the core, whether there was a compact core or no core. And instead what we found was that it really looks fuzzy. There may be a core there, but it's very big, and it may be partially dissolved, and we're studying that, but that came as a big surprise to us that there was no core. Now these mysteries that have to do with the interior extend into our magnetic field experiment, and I want to turn it over to Jack Cannerny, my colleague, who is the lead for the magnetometer experiment, as well as the deputy PI, to explain the magnetic field discoveries.
Thank you, Scott. I'd like to start off with the magnetic field observations. First off, the magnetometer is it's like a fancy compass, an electronic compass. It measures both the direction of the magnetic field, like a compass does, and it also measures the amplitude or the magnitude of the field. Now, the Earth's magnetic field, we have a pole in the north and a pole in the south, and in between it varies little. Wherever you go on Earth, the compass needle does not deviate very much from north or south. And that was kind of our expectation for Jupiter before Juno's observations, based on our knowledge from spacecraft that passed not so close to Jupiter. And Juno really is the first time we got in close, very close to the surface of Jupiter. And what we found in our first few passes is that the magnetic field was both stronger than we expected, where we expected it to be strong, and it was weaker than we expected when we expected it to be weak. In other words, it evidenced a dramatic spatial variation that we were not quite aware of previously. To illustrate that, I'd like to turn to Jack 1, which is a figure drawn up by our grad student up at Harvard, Kimmy Moore, and she's represented on this sphere the magnetic field that we expected at Jupiter, and those are the contours that extend from left to right, the red positive contours up north and the blue negative contours down south. On top of that globe, there's a trajectory, the subsurface latitude and longitude of the spacecraft during PJ1, and those 5 groups of different colors represent the kind of addition to the magnetic field that you would have to make to follow the field along the trajectory. So it just illustrates the spatial variation of field that we see moving along the trajectory close to Jupiter. And we've seen that now on subsequent periapses, and of course this is just a notional representation, but it's very significant because when we see this kind of small spatial scale variation, it indicates to us that we may be very close to the source. And so that might mean that the dynamo is above that metallic hydrogen region that you saw in Scott 3, and it may operate in the molecular hydrogen envelope above there. So that's very significant. But I'd like to turn to some of the observations of the aurora. If you can go to Jack 2, we have a little movie showing the ultraviolet emissions from the South Pole collected by the UVS spectrometer as it flew above the pole. This is the first complete image of the South Pole that we have because, of course, all previous observations were made near the equator plane, never from atop Jupiter's polar region where we could stare down and look at the aurora. So this is an amazingly complex aurora in the South Pole. It has many components that we expected to see there. The very innermost circle you see is the main aurora. Then there are very substantial emissions around that main aurora, extending all the way down to the emission that you see just to the left in this still, which is Jack 3. That's caused by an interaction with the satellite Io, the innermost satellite in Jupiter's magnetosphere. And that long tail extending past Io, that simply traces out Io's orbital motion about Jupiter. And the very significant the thing about this figure are the reds and the whites and greens. Those colors represent a different path length through the atmosphere for these photons, these ultraviolet photons. And inside the main aurora, we see emissions that are largely red. That line between the red emission and the white emission, that follows the sun around and illustrates a solar wind control of the aurora that we were not quite prepared to expect. But more significantly, it looks like we can interpret those reds and whites in an entirely different way than we have previously. It looks like the red emission might evidence electrons being sucked out of the atmosphere instead of precipitating in. And we normally attribute auroral emissions to electrons precipitating down onto the ionosphere. But instead, it looks like some of these emissions are actually driven by electrons being pulled out of the atmosphere. So that's intriguing. I have to move now to my final graphic, which is Jack 4. I want to talk just briefly about the trip from Earth to Jupiter. We spent 5 long, cold years in space in transit to Jupiter. During that time, the star cameras that we use to provide attitude information for the magnetometers, they looked out into space continuously, and occasionally they saw things flying by that weren't in the star catalog. And what we found is that we could track some of those objects, and indeed they were excavated from the solar panel by the impact of dust particles. Now these are tiny particles. You could fit 100 of them on the head of a pin, but they're traveling at enormous velocity. They're 10 times the speeding bullet. And so they excavate little pieces from the spacecraft, and those float off, and we see them in reflected sunlight. So it turns out that we can use this spacecraft and its prodigious 60 square meters of solar array as the largest dust detector ever flown in space. And so we're sensitive to particles that are larger and more infrequent than those that can be measured in space by a dedicated dust detector. So that's exciting. Not to worry, the spacecraft is operating fine. It turns out all spacecraft traveling this path are pelted with numerous impacts. We recorded close to 1,000 of them on the way out, and we're still operating fine. We're just the first spacecraft that's able to see what happens. So I'd like to turn this over now to my colleague Heidi Becker to talk about the radiation environment. Heidi?
Thank you, Jack. And to start, I'd actually like to keep on the theme of star cameras and share a very special picture with everybody that we took with our Stellar Reference Unit, which is the spacecraft star camera. This is our navigation camera that takes pictures of the stars to guide our way. So if everyone would go ahead and start Heidi 1, which is our animation, what you see is where we took this image, and it was in a very special place. What you're seeing is Juno flying in between the narrow gap between the planet and the radiation belt. And as we turned out, the star cameras took this picture. And if you go to Heidi 2, you'll see the still of that. And what you're looking at is the view of the constellation Orion from inside Jupiter's ring. And this is the first image of Jupiter's ring that has ever been collected from the inside of it looking out. Juno is 3,000 miles from the planet when we took this picture, and what you're seeing here is the main belt of Orion in the center, or in the main belt of Jupiter, actually, main ring, in the center of the image. And the bright star in the upper left is Betelgeuse, and the 3 bright ones in the lower right-hand side of the image is Orion's belt. So what you're looking at here is a ring of dust that's 40,000 miles away and stars that are hundreds of light years away, all in the same picture. And if you go to Heidi 3, we've connected the dots for you so you can see Orion there. It's very recognizable. This is what it looks like when you see it from Earth. And we thought it would be nice to share with everybody that you could be 500 million miles away from where we stargaze at Earth and look at this, stargazing from Juno. And heaven looks the same to us from Jupiter. So, and there's no radiation in that picture. but that isn't true everywhere at Peridot. So if you will go to Heidi 4 and play this animation,
and these 14 images, the width of the image is the width of the JunoCam field of view. But we collect our images as the spacecraft spins. So as the spacecraft gets closer and closer and closer to Jupiter, we see less and less of Jupiter itself in terms of area, but we see more and more detail in the pictures. And so I am going to actually show you the fourth image in the sequence from the left to start with, and then the fourth from the right. So just picking out two of those 14 to look at in this higher detail. So if you go to Candy 2, this is taken at approximately 38 degrees north latitude, and you can see a big wavy band of clouds in the middle of the image. If you go to Candy 3, I'm drawing your attention to those clouds, and then in Candy 4, it's really just a cutout of that same image. But there's a couple of things I wanted to point out here. So we've got these big wavy clouds, but then you can see tiny little white dots. They look tiny just because Jupiter is so big. These are actually clouds that are about 50 kilometers across. They are up above the cloud deck. We know that because we can actually see them casting little tiny shadows. And we've seen this actually before in some of our earlier images, but in this particular perijove, the lighting is really good to see these features, and we have our camera settings dialed in, and honestly, we were so enchanted by the poles that we're only now just starting to look at other places on the planet. So these look almost like squall lines. If you go to Candy 5, this is an image taken now in the southern hemisphere. This is the South Tropical Zone, and again, I'm going to go to the cutouts that show you in more detail what we're looking at. So Candy 6 and then stop at Candy 7. Here you can see again that it's a really stormy day on Jupiter. We've got these little white storm systems really just scattered across the entire South Tropical Zone. Again, they're about 50 kilometers across, which is, so I keep saying tiny, but they're really not tiny at all. And they're up above the cloud deck at a pressure level where the temperature is going to be very cold. And so what you're seeing is most likely ice crystals of water ice and ammonia ice. I want to mention that these images that I just showed were processed by two of our amateur citizen scientists, Gerald Eichstadt and Sean Doran. They have processed quite a number of our images, but it's really the whole endeavor of JunoCam was to find ways for the public to participate in a meaningful way on a flight mission. So with that, I'd like to draw your attention to Candy Hansen number 8. And what you'll see is across the top, I've got 4 images of Jupiter. This is just 4 of many images that our amateur astronomer community has contributed. So on our website, we have a way that the community can upload pictures taken from their backyard telescopes. That's the top row. Then we take those images, and again, many more than 4, and we make a cylindrical map, which is what you see along the bottom. Then for a given perijove pass, and in this case it's number 6, we ask the public to define points of interest, places they think would be good spots for pictures. And so that's what the yellow circles represent. And the 2 images that I just showed you are the ones that are covered by those green circles. So we the public voted on what to take pictures of. We ended up with those, and so our whole citizen science endeavor, I think, is turning out to be quite interesting. The last chart, Candy Hansen 9, we love to see artistic products in addition to the more rigorous renditions of color reconstruction and so on. And the thing about art is that it captures feelings that either you don't recognize in yourself or maybe you don't know how to express. And for me, this image captures how I feel to be a part of this project. And I'll just mention this was processed by Myrna. With that, I'm going to turn it back to Scott to give us a little bit more.
So thanks, Candy. I'm always amazed at looking at those pictures. The idea of seeing those little cloud features, those white caps coming out of Jupiter, I mean, they're full of ammonia and water ice, and you know what you're really watching is it's snowing on Jupiter, and we're seeing how it works. And so I can imagine myself flying around in that atmosphere while it's snowing, and it's really great to be able to project myself and use that imagination and understand how another whole world works. Some things are similar, and a lot of things are different. And you know, your last picture of the art really shows how people are able to artistically express themselves. And it's so great that we can do that and enable that with the Juno. We have a big campaign with Juno for public awareness where we're trying to inspire and motivate the connections between science, art, and music. And a lot of the images that are being made on our website by the public are actually artistic. Some of them are science, and a lot of them are artistic, and it's great to see that. And that whole collaboration that we do extends into music, and we've formed a collaboration with Apple, and we've made some music that's Juno-related, and Apple's helped us distribute that. And what I'd like to play for you next is some sounds that we got that we received on TJ4, the fourth time we flew by Jupiter, and we've been studying those, and we want to share them with you because they really echo and demonstrate this connection between science, music, and art, in the sense that these sounds sound a lot like musical notes. So you can take a listen to nature's music here with going to Scott Bolton slide 7. Now that's a audio video file, and you have to click on it to play. You may have to turn up your sound, or you can listen to it through us. Wanted to share these with you. So I'd like to go to Scott Bolton 8, sort of to close. This is a picture of Jupiter that's also posted on our website. We open it up to amateur astronomers who help us actually plan out the JunoCam images. And this was taken by Christopher Go and posted. It's a pretty recent picture of Jupiter. And what I wanted to show is this looks like the Jupiter that we know and love. It's got the zones of Belts and the Great Red Spot, and I want to extend an invitation to all of you to join our team as we look forward to the very next close polar pass by Jupiter when we'll be targeting that Great Red Spot. Now, that Great Spot's moving around, so it's not the easiest thing to target, but on July 11th, we're targeting to fly right over that. So stay tuned, and you can join us on July 11th. Thank you.
All right, thank you, Scott, and thank you to all the panelists. We're going to be ready to take some questions from reporters, and we'll try to grab a couple from social media. A reminder to reporters, if you do have a question, please press *1, tell the operator your name and your affiliation. And I do want to mention that this media telecon will be archived afterwards with visuals on Ustream at www.ustream.tv/NASA JPL2, and I'll give that out once again before we wrap up. Let's go to our first question, which comes from Alan Boyle of GeekWire. Alan?
Hi, thank you. I guess this would be a question for Scott. What do you think are the factors that have led to these surprises? How did you get things so wrong, I guess, would be one way of putting it.
So I think we're all sort of feeling the humility and humbleness of nature. I think a lot of scientists, when we looked out at the giant planets and we saw that they were, so big, these giant big gas balls, was that a lot of Earth works through the sunlight, generating dynamics in the atmosphere, and a lot of assumptions were that once you turn off that energy, that maybe everything would be uniform and boring. And I think that we were just wrong, and so this is making us rethink how giant planets work, not just in our own system, but giant planets are really important throughout the galaxy and the universe. I mean, we see other planetary systems, and a lot of them have giant planets, sometimes many times bigger than Jupiter even. And we're getting the first really close-up and personal look of Jupiter, and we're seeing that a lot of our ideas were incorrect and maybe naive, that it's very complex. And it's really, there's a lot of deep motions going on, and there's a theme here. There's motions going on just beneath the clouds that we see with the microwave, and there may be very deep winds and deep motions going on that we see with the gravity field. And it's hard to say yet, but more data will tell us how deep those really go. We're just at the beginning of this mission where we're going to map out that planet.
All right. Thank you, Scott. And then we're going to take our next question. And actually, before I do, I just wanted to ask reporters, because we do have quite a few of you in the queue, to keep their question to one question, if needed, one quick follow-up, so we can go through the first round, and then afterwards, assuming we have time, we can go back to everybody. Anyway, but that was fine, and Alan Boyle, you did not do that, so you did not do more than one question, so it wasn't intended at you. All right, let's go ahead with a question from Marcia Dunn at Associated Press.
Yes, hi, for Dr. Bolton. The larger splotches at the poles, not the oval cyclones, but those other weather systems that are thousands of kilometers across, what are those? And for the cyclones, do you have any idea how powerful they would be? Lots more over Category 5, and how many cyclones altogether would you guess?
So I haven't done a count of all those cyclones, but there's lots of them. I mean, you could count them yourself. There's dozens at least going through the system. These large pieces are other dynamic features. I don't think I can explain exactly how fast any of these are going. We haven't measured all the velocities for each of these cyclones. Of course, it takes multiple images at different times in order to get that kind of dynamic information. And so I think those are objectives that maybe we'll be able to accomplish as we go over the poles multiple times. And over Perijove 6, the one we just took, we designed it, once we saw those cyclones, we basically set out to take images so that we could try to measure some of those velocities that you're talking about. But I think, a lot of this was so new. We really just learned that Jupiter really is like this from this data. And now the hard work comes with the theories to try to explain why and how is this kind of is these dynamics manifested, and how are they maintained, and are they stable? And these are questions that I think are new objectives for our mission as we move on and get more data.
Quick follow-up, these dynamic features that are so much bigger than the cyclones, could they also be cyclones, like mega-sized cyclones?
They could be, although they don't appear to be gigantic cyclones. They don't have the same morphology that I would be used to, but I think that those kinds of questions, I think we would be better off pointing you toward our atmospheric experts rather than me.
Okay, thank you.
All right, thanks, Marcia. And then we're going to move on to Bill Harwood of CBS News. Hi, Bill.
Hey, thanks. For Scott, can you expand a little bit more about the core? I'm not really sure how to visualize a fuzzy core. I realize you don't have a solid answer to this, but any expansion would be great. And for Candy, on Candy Hansen 5, the width of that band, that whitish band with all this stuff, it looks so much broader than the normal belts we see from equatorial views. I'm just wondering if it's the orientation that's throwing me off. I'm not really sure what I'm seeing there. Thanks.
Why don't we let Candy go first?
Okay, yeah. So when we're close to Jupiter, we do not see horizon to horizon. So we're only seeing, a limited range in latitude, and that's why it looks so odd. And if you look at the sequence of 14, you can literally, the way to think about it is if you were looking through JunoCam's camera lens, riding on this spacecraft, you start out at a distance say you were looking at your hand at a distance. Now you pull your hand into your nose. That's what it's like. And so we are only seeing just the south tropical zone at that point because we are so close to Jupiter.
Okay, thank you. And we're going to go now to Mike Wallace.
Wait.
I think I owe him a question on the core, an answer.
Okay, sorry about that. Go ahead.
So, the fuzzy core idea. So, scientists, when they've done models and what we were kind of expecting to see at Jupiter, there were two extreme cases: a little compact core down in the center of Jupiter, maybe Earth size or 1 Earth masses, 10 Earth masses, something like that, all compact and tight in the center of Jupiter. Or maybe there was no core. Maybe Jupiter formed without a core at all. And those were the two kind of extreme models, and most scientists were in one camp or the other. And what we found was really neither are true. There may be a little bit of a compact core, but most of things, there may be layers there, and there seems to be a fuzzy core that may be much larger than anybody had anticipated. And so the gravity data that we've gotten thus far is not really consistent with just a small compact core or zero core, but it is somewhat consistent with a large fuzzy core that may be partially dissolved, and it's also consistent maybe with some deep motions or zonal winds and things like that may be going on that are dictating the interior of Jupiter's dynamics, which maybe are very different than what historical models have assumed.
All right, thanks. We're going to go to Mike Wall at space.com.
Thank you, guys. This is all, that's just like really, really interesting. This one's probably for Scott or also for, it can be maybe. Scott, like you said that those clouds, it was snowing on Jupiter. Is that water ice that we're talking about? Snow that like we're used to here on Earth, or is it some kind of exotic substance? Is it something we would recognize?
It's probably mostly ammonia ice, but there may be water ice mixed into it, so it's not exactly like the snow that we have. I was using my imagination when I said it's snowing there. It could be hail.
Great, thank you.
Okay, we're going to jump over to Ken Chang with the New York Times. Ken?
I was wondering if, this is for Jack, if you could explain the physics of how electrons could be sucked out of the atmosphere to create the aurora.
Okay. In that picture, we had always assumed that if the ultraviolet emissions are coming from deeper in the atmosphere, which is what that color represents, that it was simply due to particles that were so energetic they were penetrating deeper than the rest of them. And we really never, should have perhaps, but never considered the idea that, well, maybe they're just being accelerated out of the ionosphere. And indeed, when we crossed the polar cap, the electron detector, JEDI, measured electrons moving up away from Jupiter across that entire inner circle. And so putting the two together, we now recognize that what we see in red, it probably shows us that electrons are being pulled out of the atmosphere by an electrostatic potential. Electric potential is what do that. We put a voltage on the field line and an electric field and draw the electrons out of the ionosphere. And as they're leaving, they collide with the hydrogen molecules and excite ultraviolet emissions. So it's a 180-degree turnabout from the way we were thinking about those emissions prior to the Juno observations.
Okay, we're going to switch over for 1 second to social media. We have a question from Jorge Vidal on Facebook asking if you've seen the cyclones observed near Jupiter's North Pole change when you compare pictures of different flybys.
Yeah, the quick and simple answer is yes. And in fact, we were just puzzling yesterday over trying to see if is this one the same as that one, or is that one the same as this one? So yeah, they do change.
All right, thanks to Candy, for that reply. And we're going to take one more right now from Twitter. Tori is asking if Jupiter's magnetic poles are really far from their axis of rotation.
Yeah, this is Jack. The magnetic poles for Jupiter's magnetic field are really quite similar to the Earth's. The poles are offset by about 10 degrees. But what's different, of course, is the small spatial scale features that we're seeing now that have to account for the differences in what we're measuring. And to use that Earth analogy again, if we were to follow along the surface of Jupiter along that track with a compass, we would see it deviate left and right, much more so than when we see moving around on the Earth. The more complex, lumpier magnetic field. But overall, the broad scale, as you step away from Jupiter, we would call it a dipole field. That's really quite similar to the Earth's dipole field, only much, much stronger.
Thank you, Jack. We're going to take a question now from Spaceflight Insider and Ocean McIntyre. Ocean?
I'm just wondering, on Scott Bolton 3, you have this large amount of metallic hydrogen. Is there an estimate at this point of the percentage of the planet that is made of metallic hydrogen versus molecular hydrogen?
This is Jack again. The current models place the molecular hydrogen transition to metallic hydrogen down at about 0.75, 0.8 planet radius, and this is where the pressure, about 2 million times the atmospheric pressure on Earth, is so great that it squeezes the electrons off the nuclei and they're free to move about, much as they are in a metal. But that's at about 0.75 or 0.8 of the planet radius, and it depends on our knowledge of the behavior of hydrogen under such extreme pressure and temperature. This is about the pressure that we can achieve on Earth in a laboratory with a diamond anvil. So it's an area of intense research right now, and they're just getting to 2 megabars where we can see stable metallic hydrogen.
Thank you.
Our next question is from Kelly Beatty at Sky and Telescope.
Yeah, thanks very much. Scott, I hope at some point you tell us which of those plasma waves are from the monoliths or not. This is actually for Heidi Becker, and I'm wondering, you said that there's a gap at the inner edge of the radiation belt that you expected. Why do you expect that there is a gap there? Why doesn't the radiation belt go all the way to the planet?
Well, what keeps the electrons trapped in the magnetic field is a kind of a special cocktail of their direction relative to the magnetic field and their energy relative to the magnetic field strength. So it kind of has to be just perfect to stay trapped. And if it's not, those electrons will just keep on going and go into the planet and be lost. And as you heard Jack talk about, there are all of these kind of strange non-uniformities in the magnetic field. So we expect there to be some region where electrons have gone into the planet and been lost and that it will be empty. So we did expect, based on that theory, that there would be a gap. But we were just crossing our fingers that there would be for Juno. And there is.
So if I could just follow up, are you saying that very close to the planet, the notion of a dipole field breaks down and it becomes a higher order field that allows the electrons to be lost?
Yes, in some sense. I mean, we have an offset tilted dipole at Jupiter, this is Scott, to some extent. And so, you know, as these electrons move around the planet, they're trapped in the magnetic field, but the magnetic field is not perfectly aligned with Jupiter's spin axes, and it's all set a little from the middle. So as they go to one side of the planet, they get a little bit closer to the atmosphere than on the other side, because they move around in constant magnetic field strength. So on one side, they're going to smash into the atmosphere before they smash into it on the other side. So they're going to create a little bit of a gap.
I got it.
The other thing that creates the gap is that they're radiating their energy away very, very quickly due to synchrotron emission. The high energy radio emission that comes out from relativistic motions of these high-energy electrons. And so as they get close to the planet and the magnetic field goes up, they start radiating away. So those two processes kind of compete against each other to create the gap. And we knew there was a little bit of a gap there because the Galileo probe showed evidence of a gap as it went in, but it only sampled one spot. And there's a gap like that at the Earth's radiation belts as well.
All right, thank you. Next question is going to come from Mental Floss with David Brown.
Hi, this question's for Scott. Having collected so much data that challenges fundamental assumptions about Jupiter, how does that affect future passes by Juno?
Well, they make them more exciting. But, I mean, the truth is that we've just started to scratch the surface. We have one of the great things about exploration is that you go to a place that you've never been before, and you invent new instruments and new kinds of ways to make measurements, and you discover things that you never could have anticipated. I mean, that's the whole point of exploring and learning. And so we went, and of course we're up close and personal to Jupiter for the first time, and we have some very unique instruments and some that have been invented basically for this mission, and we saw brand new kinds of things. Now the plan always was to go over and map the planet, so we want to go over many different longitudes and eventually learn how the planet looks all the way around, and that's really what tells us about how it works inside completely. And so what we've seen is we're surprised. And in fact, all the data really points to the fact that we need more the rest of our mission in order to really figure out how Jupiter works. The good news is that we also have confirmed that Juno's the right tool to do this. We have the right set of instruments. We have the right orbit. We actually are going to, win over this beast, and we're going to learn how it works. But it's going to take time. And we have to be patient in order to unravel the mysteries, because many of them are wrapped into how does Jupiter look at different longitudes or in different time periods. And so we have the right tool to do the job. And so we're not going to change our observing strategy necessarily in order to accomplish the answers to these questions. But we are changing the models, and more data, of course, goes in to constrain it. And so that's how science works. We will modify some of the imaging in order to try to measure the cyclone speeds and things like that.
All right, we're at the top of the hour. We can go a few minutes past to wrap up a couple of questions that have been waiting. Here's sort of a last call for reporters on the line. If you do have a question, please press *1, and we'll get you in the queue for a couple of final questions. In the meantime, let's jump in for a follow-up from Ken Chang, New York Times.
Oh, thank you. I was wondering if you managed to do any comparisons between the Juno data and what Cassini's getting at Saturn.
We absolutely plan to do that. In fact, I'm glad you brought that up. It's a great question. So I'm on the Cassini team. Many of us on Juno are on that team as well. And back many, many years ago when we first started to develop Juno, I went to the team and said, why don't we try to take Cassini at the end and go into a Juno-like orbit? And we could, learn about both planets in a similar fashion. Now, Cassini doesn't have the exact same kind of instruments we have, and of course we're tuned to do this interior research, but it has a lot of great instruments that can learn a lot about the interior and other things that it can do close up. And so after a while, the Cassini team and NASA all got behind that, and of course Cassini's in that mode now. It's exciting because we have 2 spacecraft orbiting 2 of the giant planets in the system, and we're both doing these close polar-like flybys. And so there are plans. Of course, we're both trying to figure out our data from our own planet at the moment, but eventually we will compare. And of course, that's the key to scientific advancement, is comparative study. So being able to compare Cassini's measurements at Saturn and Jupiter's measurements by Juno, we will really be able to advance our understanding of how these giant planets work.
All right, we're going to take a question now from Amina Khan of the Los Angeles Times.
Hi, I just had a quick question. You mentioned that the radiation levels were about 10 times lower than expected, which is good news. Does this have any implications for the orbit? Might you go back to some of these shorter orbits if it seems like it's less damaging out there?
Well, this is Heidi. Hi. The place that I was referring to is this really brief, sort of 2 15-minute blips that we have very close to the planet. Our orbit is a lot bigger, and it's great that the levels were appearing to be 10 times less close to the planet, but that's not all of the orbit. So there's a lot more data from further out, and the really nasty part that we're going to get into later is near the equator, further out from where I was talking about. So it's a little early to speculate on levels. What we're seeing now is very good. The spacecraft is behaving very well. But we can really only say right now that what we're seeing close to the planet is certainly much less than what we thought would get in.
Thank you.
All right, thanks. And we're going to take one final question from social media, and then we'll wrap up with one or two media questions. And again, to remind you that the audio with the visuals of this telecon will be archived on www.ustream.tv/NASA JPL2. That's the number 2. Okay, and then also any reporters who have not had a chance to ask a question when we wrap up, you can call us here at the JPL newsroom, which is 818-354-5011, or at NASA headquarters newsroom as well. And I'll get you that number when we wrap up. All right, so in the meantime, we are going to take a question from Twitter, and the question is from Leonardo, who asks, why are Jupiter's storms so big?
Well, Jupiter itself is really big. So I think the scaling, if you compare the size of storms on Earth to the size of the Earth, the size of storms on Jupiter to the size of Jupiter, I don't think it's really unexpected. I think that the scaling sort of works in a very, very rough way.
Okay. We're going to go back for a quick question from Sky and Telescope, Kelly Beatty.
Thanks very much. This is for Candy Hansen. Candy, I've been following a lot of the amateur processing of the images and the interaction with the team. Can you characterize how valuable the role of amateur astronomers has been in creating targets and actually enhancing the science? Is this the most intensive interaction that you've had on a mission?
Yes, it definitely is. We have a very tiny ops team, and the contributions of the amateurs are essential. I cannot understate how important the contributions are. We don't have a way to plan our data without the contributions of the amateur astronomers. We don't have a big image processing team. So we are completely relying on the help of our citizen scientists. And in fact, the data interpretation as well. We have people jumping in to help us with that as well. So if you go to the image processing section of the Mission Juno website, you will see that we have over 900 contributions of images that have been processed by members of the public. And what I find really actually the most phenomenal of all is that this takes real work. When you download a JunoCam image and process it, it's not something you do in 5 minutes. The pictures that we get that people upload back onto our site, they've invested hours and hours of their own time and then generously return that to us. So it's really been remarkable.
Thank you.
All right, and our last question comes again from Ocean McIntyre at Spaceflight Insider.
So regarding the thermal information, I know the microwave radiometer has been tracking some of that information, getting that data. Has there been anything regarding the different thermal information, or thermal data for different layers within Jupiter?
Not sure I understand the question. You mean in addition to the microwave instrument?
Well, I know that the microwave instrument is also looking at the thermal emissions. Has there been any data that's come back or that's different than what you expected to see?
Yeah, well, I mean, the way the microwave emission works is that microwave wave radiometer works is we're looking at thermal emission coming out of Jupiter, and so the data that I presented on slide 4 is really the microwave emission. We're interpreting it and showing it to you in terms of ammonia abundance, but we're really looking at brightness temperatures which are related to the temperatures inside of Jupiter's atmosphere. And so that's exactly what we're looking at and showing you the variability on. And then we have another instrument that was built in Italy called GIRAM that also looks at thermal, but it looks at the top part of the clouds. It doesn't penetrate down like the microwave does. And we have maps and we publish data associated with the thermal emission from that as well.
Okay, thank you very much.
All right, thank you. That wraps up our Q&A and actually wraps up this whole event. I want to thank our panelists today for some super interesting stuff, and thanks to all our media and social media followers who had some excellent questions. And again, a reminder that you can rewatch this. It should be posted shortly on www.ustream.tv/NASA-JPL2. Any follow-up questions from news media, again, to JPL Newsroom, 818-354-5011, or Lori Cantillo at NASA headquarters at 202-358-1077. That's 202-358-1077. And, of course, there's lots of info about Juno online at www.nasa.gov/Juno and also at missionjuno.swri.edu. And we do have the press release that just went out a little while ago, and that is now posted on the Telecon page. Thanks, everybody, for joining us, and have a great day.